Alright, so this will be the next section, which will be atoms. Now, so where this was first proposed, where you first started hearing about atomos, which is the root that you get atoms from, that's the root word, was around 384 BCE, so BC, before Christ. Aristotle said that all matter is composed of four elements and all matter is continuous, not atomistic. So this started a debate, if you will, or a discussion within Greek natural philosophers. And this actually sparked many of the ideas that then went forward, got tested later, because the Greeks never tested anything. It was considered, you were considered not to have any confidence in what you were trying to sell or say if you actually bothered testing anything you said as a Greek philosopher. So, but eventually it did get tested, and we found out which one actually made some sort of sense, which is our modern theory of atoms. 450 BCE. Now I'm gonna murder these names because I don't have very good tongue for Greek. So Lysippus and Democritus said that atomos, the point at which matter can be no longer subdivided, existed. So if you were to try to cut up, according to Aristotle, if you cut up something infinite number of times, it would just keep subdividing. So you could take water, you could cut it up an infinite number of times, and it'd still be water no matter how small it got. However, these two philosophers disagreed. And so they said that if you cut it enough times, you're going to get to a smallest base unit. And those were the atomos that they thought existed. And that is that these were supposed to be indivisible. You couldn't divide it anymore. And so if you cut up sand enough times, you would get mini sands, essentially, right? If you cut up water enough times, you'd get the smallest point at water exists, and then you could not cut that any further. That was as far as you can go. Now, in the early 1700s, Lavoisier, and remember that really until the 1800s, most people that were really doing serious sciences at that point had some sort of roots in French culture. That were the place science was being done in the 1700s. So Lavoisier came up with the law of conservation of mass. And so during a chemical change, matter is neither created nor destroyed. I know that you probably are used to thinking in these terms that you use power, it came from somewhere, right? You use gas, it came from somewhere. But when he proposed this was actually extremely radical. And he actually got a lot of flack for this, and there's a lot of arguments. So it was quite a radical conception back then. Keep in mind that back then people literally thought sea monsters just popped into existence. Or you could open your closet and it could have a monster in it, a demon in it, or it could have a gold or an angel. Who knows? Not your coats necessarily. All right, so this law of conservation of mass was incredibly important because it said that if you took something like mercuric oxide and you separated the components of that, so you separated out the mercuric oxide into the mercury and the oxygen it was composed of, that you would have an equal mass on both sides here. So if you had 100 grams of that mercuric oxide, you would end up with 92.6 grams of the mercury and 7.39 grams of the oxygen. And if you added these masses up, you would get your original mass. Now, do keep in mind that yes, he understood, and yes, we understand, that if you actually tried to do this, you oftentimes lose things because you let some of the gas escape, or you drop some of this on the floor, okay? So you never truly get the 100 grams because in real life, because you always lose stuff. You always mess up. 1799, Proust had the law of definite proportions. So a compound always contains the same elements in certain definite proportions. Now that's very nice because the law actually says exactly what it means. So the name and what it means are the exact same. And they've sort of given us a really nice thing that happens in chemistry, and that is we always try to name things exactly what they are. So if you ever hear the naming in chemistry, it is what it says. Now, this law of definite proportions, this is actually something that people still don't understand. Uh, if you were to look at major financial political groups in the world, I've had people that have gotten, you know, 3 semesters of chemistry on their belt and they still don't fully grasp and have let this percolate through their thought process. And so, law of definite proportions, first off, is a law. What a law means is laws are something that we see every single day. And so they have been repeatedly proven to you every single day, every single moment of your life. And so, yes, a law is something that typically is not going to be undone because it has been tested trillions of times, not a few hundred times or a couple times, like most theories would be. Now, the law of definite proportions is one that you probably know of. So, for example, what is water? Water is H2O. You've probably all heard that before. Water is H2O, or carbon dioxide. You've heard of that before. Carbon with 2 oxygens. And you guys probably know these from various parts of your life. For example, carbon dioxide, you probably have heard of that in terms of like global warming. Uh, Now, you knew that. You knew the carbon dioxide was named carbon dioxide. You probably even knew the formula of it, CO2. But here's the thing that's really funny. Now, this law, a compound always contains the same elements in a certain definite proportions. Well, that also goes the reverse way. If you have the exact same proportions, it is the exact same compound. So if you have 1 carbon, 2 oxygens, no matter where it comes from, that is carbon dioxide. It has the same properties, it does the same things. That is carbon dioxide, period. And so one of the things that made me realize that I need to start being extremely explicit and not assuming that students necessarily pick up the words I say and I give a little bit of thought to it is that not only did I have a student that didn't understand this, but after 2 semesters of people teaching and these concepts, I've had some rural students actually didn't realize this. Uh, I also had Greenpeace that had a political spokesperson on, and they said this. And so then I went to their website and realized, oh my God, they didn't understand the law of definite proportions. A multi-billion-dollar a year political lobbying group didn't understand a basic concept that everybody should understand. And this is that they said that the CO2 that comes out of a human being or the CO2 that comes out of an animal is better for the environment, is not a greenhouse gas. And that the CO2 that comes out of a car is a greenhouse gas. Uh, okay, so if we think about that, that doesn't make any damn sense, does it? Literally, they're the same thing. By definition, they're the same thing. By what you just said, when I said that entire statement that was on their damn website, they're the same thing. So the carbon dioxide that comes out of a human, a factory, a car, those are all greenhouse gases. Those are all the exact same damn thing. Now, what they probably, I would hope, I can't speak for them because I mean, they really might have thought that CO2 period, if it comes out of a human, is different than it comes out of a car. But what I would hope that they thought is that the CO2 mixture, so when you breathe out CO2, you're breathing out things like oxygen, CO2, there's a bunch of nitrogen in there, that mixture was better for the environment than what is given out of some cars. Though, interestingly enough, if you have a properly functioning catalytic converter, the mixture that comes out of the tailpipe actually isn't that bad. It just has a lot of CO2, and we really can't afford that much CO2 in the atmosphere anymore because we're just producing too much. but CO2 is actually fairly benign other than its role in the greenhouse effect and global warming. Though interestingly enough, if we did not have enough CO2, it would also be just as bad. But that is not a concern right now. All right. So regardless of the source, copper carbonate, always has the same composition. So right here we see different sources of copper carbonate. We see a very beautiful rock right here that's this greenish color. We see this patina that's on a building roof, copper roof on a building. And this is just a copper carbonate we've made in the lab. And you can see they all have pretty much the same color. It looks a little different because the lighting conditions and how we layer it is different. So these always have the exact same composition. It is the copper with the carbonate, which is CO3. All right. So Berzelius' experiment illustrates the law of definite proportions in a very nice manner. So in this experiment, we took 10 grams of lead. We reacted it with just enough sulfur to completely react all the lead away and make this. This is lead sulfide. This is the what happens to lead if you leave it around long enough. It becomes like that black color on it. That's the lead sulfide. Okay, so 10 grams of lead with 1.55 grams of sulfur gives you 11.55 grams of lead sulfate. Notice that again, we conserved our mass. So 10 grams of lead, we put in 3 grams of sulfur, and what happens? Well, what we find out is it only uses 1.55 grams of that sulfur to make our lead sulfide. Once we've used enough sulfur to completely use up this lead, the remaining sulfur is just leftovers. It's excess. And what I want you to think about whenever you see a chemical reaction like this, and that's what that is, it's a chemical reaction, is this is just a recipe, okay? That's all that is. Cooking is chemistry. Whenever you are putting like hot dogs with hot dog buns, that's chemistry too, okay? You're cooking the hot dogs, you're putting them in the buns, that's all it is. It's math and chemistry. So, if we have 8 hot dogs, we need 8 buns, right? It doesn't matter if we had 20 buns, we still only need 8 buns for our 8 hot dogs, do we? Yeah, we'll have leftover buns, but that won't matter. And that's what you're seeing here. It's the exact same principles. Now, right here, we see that we have 18 grams of lead. Notice we've increased the amount of lead now, but we're keeping that sulfur the same as the first time. And what we see is that the sulfur will get used up now, but the extra lead won't. So we'll again only make 11.55 grams of lead sulfide. But now we're going to have 8 grams of lead left over. Now you may be wondering why I show you these experiments and try to make you understand how these laws were generated. There's actually 2 reasons for that. Number 1, I'm trying to help you build up your critical thinking skills. Meaning that if you run into a situation in your life and all you know how to do is Hulk smash, then every single problem in your life is going to become Hulk smash. You're going to try to, break it. You won't have any other skills to use. But if you've seen different approaches to try to prove or disprove something, then you're going to have more tools that you can try to apply. And you can adapt these things to other situations in your life. Okay? All right, the other part, what I'm trying to do is when I show you the experimentations, you'll oftentimes hear political, essentially people are trying to sell you something, but whatever. Politicians and political figures say things like, you're just taking those elite, I'm elite, I guess, huh? That's kind of laughable. Anyways, those elitist views, and you don't know why you're doing it, you're just parroting them out because you were taught those. Well, scientists, a good scientist and a good science teacher should hopefully give you enough information that you could go back and explore that view and see if it's right. Okay? You should be able to, every time I give you something, be able to go back, reason it out, and see if I'm wrong. And if you find me wrong and you can actually go ahead and prove that, I'd be extremely happy. because again, that would lead to big breakthroughs if we found fundamental concepts in chemistry wrong. That'd mean huge breakthroughs. And so I'd actually be very happy if you did, but it hasn't happened yet. Anyways, it hasn't happened to me yet, but it did happen just this year. So the metals versus non-metals are going to get a small different change in the next few years as they do tests. So, anyways, that's the experiment you can do. You can do similar experiments with other elements too, like iron and oxygen. The reason that this is the law of definite proportions is that this experiment probably has been run millions of times, purposefully and non-purposely, where you just accidentally did it. It's been done, probably trillions and trillions of times. I have no idea how many times. All right, so John Dalton and the atomic theory of matter. Notice this one is a theory because this is not something that can be repeatedly confirmed in your everyday life. So the atomic theory overall deals with something you can't see directly. And so, yes, we can now have instrumentation that we can see many of these things, but again, that means that we've only done it hundreds or thousands of times, not trillions. So the law of multiple proportions is again a law. Elements may combine in more than one set of proportions, with each set corresponding to a different compound. Now, I have a little bit of a joke. Hopefully you'll find it a little funny. If not, sorry. Not a whole lot of good chemistry jokes, okay? And that joke will help you sort of remember and understand the law of multiple proportions better. So a chemist is hanging out with his friends in his garage. And so the chemist goes over to his kitchen and yells back from the kitchen, "Hey guys, does anybody want some H2O2?" And so the question for this little bit of a story, the first part of this story, is why do you think the chemist went to jail afterwards? Well, if you already knew most of the stuff from this class is going to teach you, or you already understood the law of multiple proportions well enough, then you would go, well, what the people thought he said was H2O as well, right? TOO. Okay, so they thought he said, "Hey guys, did you want some water as well?" But what the chemist actually said was H2O2, as in H2, two hydrogens, and then O with a 2 behind it, which is 2 oxygens. And that's hydrogen peroxide. That isn't water. And that is actually poisonous. That's what you use on wounds. It kills pretty much any living organism if you ingest it. And so he accidentally killed his friends by giving him the hydrogen peroxide like you'd use on a wound, or you'd use to make a small little explosion that like is a loud firecracker thing. And his friends drank it. Now, hopefully, nobody would actually do that. Hopefully, you found that mildly funny. Sorry if you didn't. But that is a great demonstration of the law of multiple proportions. So, if you have CO2, that is carbon dioxide, that is a greenhouse gas that you exhale from your lungs. Now, carbon monoxide, on the other hand, with one carbon, one oxygen, has different proportions. It is a different compound, and so that is a poisonous gas that will kill you, and you definitely do not exhale out of your lungs. Okay? So you can see just a little bit of a change in the formula makes for a very big change in the effect. By the way, this is John Dalton. You're going to get quite a few of these little pictures here. He's largely regarded as one of the forefathers of modern chemistry, by the way. He was very, very, very good about doing experimentation. He sort of set how everybody does things from then on, where you'd come up with theories, you'd experiment and try to disprove them. He's a large component of that. So all matter is composed of extremely small particles that we call atoms. And so if you subdivide elements enough times, you're going to get down to the atom. If you try to go any smaller, you will no longer have that element. So if you tried to divide divide oxygens over and over and over, eventually you're going to get an oxygen atom. And that's the smallest it can go. If you cut that any further, you will no longer have oxygen. Carbon, same thing. Eventually, if you subdivide the carbons enough times, you're going to get down to a carbon atom. If you go any further than that, you will no longer have carbon. So all atoms of a given element are alike and differ from the atoms of any other element. Compounds are formed when atoms of different elements combine in fixed proportions. For example, a compound would be CO2. That's one carbon with two oxygens. Or water, which is H2O, just two hydrogens and one oxygen. A chemical reaction involves the rearrangement of these atoms. And so every chemical reaction just involves changing how those atoms are combined. For example, we can react hydrogen with oxygen, like you would do in a hydrogen fuel cell, and you would get water out of that. And that's how the hydrogen fuel cell works, by the way. So isotopes. Much of John Dalton's atomic theory has been slightly modified. The base concepts were good, but there was a lot of things he didn't understand in his time period that we have had to modify that atomic theory and express in it. So John Dalton assumed that all atoms of an element are alike, that he didn't think that there was any real difference between them. However, at this point in time, we have found that there are isotopes. And so isotopes are atoms of the same element with different relative masses. I know I said at this point in time, but really that's like 100 years ago the isotopes were found. Anyways, so they're going to have the same number of protons, the same atomic number, the same atomic symbol. For example, you can have several different isotopes of carbon. And when I say isotopes, there's sort of a common misunderstanding that happens with students. Okay, so when I say an isotope, it's not like there's a normal carbon and then all others are isotopes. All the single atoms of carbon that are different from each other are isotopes. So all of them are isotopes. The normal one's the isotope, the less common ones are isotopes. They're all isotopes of carbon, okay? All isotope means is that it's going to have a different number of neutrons. And so all the isotopes of a given element, they will all have the same number of protons, same atomic number, but they'll have different masses. And these different masses are due to having different numbers of neutrons. So a mole, or Avogadro's number. Now a mole is the number of atoms in 12.011 grams of carbon-12. So that number is Avogadro's number, which is 6.022 times 10 to the 23rd atoms. Now, one of the things I always want to point out, and I want you to understand, is a mole is like a package of something. It's like saying I have a dozen donuts, okay? A dozen means 12, doesn't it? It means you have 12 donuts. But a mole means you have 6.00022 times 10 to the 23rd atoms of something. So if I have a mole of carbon, I have 6.022 times 10 to the 23rd atoms of it. Now notice you can have a mole of anything. And if you've ever heard of Mole Day, which happens on 10/23, by the way, then you would realize that, hey, this actually can be used for anything. So on Mole Day, what they do is they look at how much, what a mole of different things would be like. So for example, they look at what would a mole of pennies be like? And the answer is it's like a really large planet. It's a lot, right? It's a big number. Or if you had a mole of Twizzlers, what would that be like? And you could stretch them to like the sun or something. I forget. But anyways, it's kind of an interesting thing. You can look it up sometime. You can look up like mole of Twizzlers, mole of people, mole of pennies. Anyways, you can have them. It's again like a dozen, right? It's like a package. So you can have a mole of anything, really. You can have a mole of atoms, mole of molecules, moles of ions, or you could have moles of pennies. Molar mass, so the mass in grams of 1 mole of a substance is known as molar mass. Notice the name actually says exactly what it is. It's just the molar, so you have mole something, mass. This value is going to be the sum of atomic masses of your elements in a compound. So for instance, if we have the molar mass of water, H2O, you could look on your periodic table. Hydrogen has a molar mass of 1. And that's on the periodic table. That's that mass of hydrogen on the periodic table. There's 2 of those, so that would be 2. 2 times 1 is 2, right? And so oxygen is then 16, 15.9999, but you get the idea. It's 16 on the periodic table. If we add 2 plus 16, that would give us 18 grams for a mole of water. Another way of representing that would be 18 grams per divided by moles. When you look at this, this means you have 18 grams per 1 mole. We don't need to represent the 1 because when you divide anything by 1, it's the same thing. Alright, so how do we use the mole and the Avogadro's number together as concepts? So the number of atoms or molecules, this is Avogadro's number, gives you moles. Now moles, if you use the molar mass, can actually give you the mass of something. So for example, if we have 1 mole of something, we know from the periodic table, for example, carbon would have 12 grams then. All right, so this is Dmitry Mendeleev. He's kind of a fascinating figure. And so he is oftentimes mentioned as the person that made the precursor to the periodic table and given a lot of credit for the periodic table. In reality, he's one of 3 people that simultaneously, almost at the same time, came up with the periodic table, or at least the concept for it. However, Dmitry Mendeleev's kind of a fascinating character, okay? So if you're ever bored one day, look up Dmitry Mendeleev. He has kind of a cool life story. It's worth reading. All right, Mendeleev arranged the elements in order of increasing atomic mass. He left gaps for yet undiscovered elements, and he then predicted properties for those elements. And when we eventually discovered those elements, and that happened, one of them got discovered like 2 years after he did this. And what was found is his predictions were amazingly accurate. They were pretty much spot on, just a little bit of error. So they were extremely good. That's one of the reasons he's credited. His predictions are really what sort of cemented it in. It's also a great way of determining whether your theory is correct or not, whether your theory is wrong. Predict things, and if the predictions are wrong, then your theory is probably wrong. Right here, this is actually his table. Dmitry Mendeleev's table, translated, of course, a little bit right here, so you can more easily understand it. But he did actually, it's funny because we didn't translate it completely. And so that's why this is table and gruppe 1, gruppe 2. Anyways, and so he arranged this in increasing atomic mass. Now keep in mind, now we know that due to isotopes that doesn't make sense. So now the modern day periodic table is arranged by the atomic number, the number of protons. But still the pattern pretty much holds the same. The masses, as you go increasing atomic number, the masses also increase. So this pattern was pretty much on target. He just, kind of got it a bit off because he used masses. So this is the one that's probably the best showing of what he did and the efficacy of it, how valuable it was. So when he did this, he predicted that there would be an element that would be below silicon. He called it ekasilicon. And he predicted it would have an atomic mass of 72, a density of 5.5. It'd be about a dirty grayish color because that was the group it was in, and he saw that there's patterns in that group, and that would be the predicted densities, colors, etc. He predicted the density of the oxide, so if you let it oxidize, that the density would be 4.7, and that if you the boiling point with chlorine would be below 100 degrees Celsius, meaning if you reacted with chlorine, it would then boil below 100 degrees Celsius. So when it was observed by Winkler in 1886, then it was observed to have an atomic mass of 72.6, a density of 5.47, which is really close, right? A grayish white color, which is again pretty damn good considering he never seen it before, it never existed before. Well, he never knew it existed before. The density of the oxide was 4.703 versus 4.7, which was amazingly good. And the boiling point of the chloride was 86 degrees, which is below 100 degrees. So he was pretty much spot on. Little error, but considering he was predicting this just from group properties, it's amazing. Really awesome. So atoms are a very real concept. It is even possible to observe computer-enhanced images of atoms now. We cannot directly observe them with our eyes. They are too small for the light to bounce off them, no matter what magnification we use, to be able to see them directly. So we have to see them indirectly, usually through computer-enhanced models. And this is why we can never really get this beyond a theory, even if it would be a law normally. Anyways, it works out. Okay, so some of the things you may have heard of before, maybe not. Green chemistry. So what green chemistry means is we're replacing rare or hazardous substances with more abundant or less hazardous substances. And this is part of the green movement. This actually, this shift away into green chemistry really started in the 70s, and it accelerated greatly in the 90s, and now it's gotten actually incredibly far. The one problem is we have not been able to scale up yet on all the green chemistry processes, so some of the industry is still lagging behind because we just haven't gotten cheap enough yet. But there's been huge breakthroughs in the last 20 years, and you're seeing a real shift towards green chemistry and it having a real impact, which is pretty awesome. So one example of green chemistry technology is the replacement of the mercury-filled fluorescent light bulbs. And so fluorescent light bulbs, if you broke their tubes, they actually would leak mercury. We now have replaced those with efficient mercury-free light bulbs. And so you no longer have mercury every time you throw away the fluorescent light bulb leaking out into your water source, which is fantastic. Okay, you guys take care. I'm going to get some another chapters knocked out and put up. And you guys have a great day.